Hello. So in the previous videos, I have explained how we can identify a regression model when you have an endogenous variable. So the key idea is to have an instrumental variable. So when you have as many instrumental variables as the number of endogenous variables, and under a few more conditions, you can identify all the parameters. And so, simply speaking, there are two key assumptions. One is the exclusion or the independence assumption on the instrument, and you have to have the relevance assumption, which means basically the instrument must be correlated with the endogenous variable, or this matrix actually has to be prime here. Zx prime, its expected value must have a matrix of rank k. Then here, first, so usually the most of the attention is paid on the exclusion restriction. So without the exclusion restriction, you cannot do anything. So when z is correlated with epsilon, then it is just another endogenous variable. So that's the end of the discussion. So exclusion restriction is really important, and you need to check if it satisfies the independence or not. However, less attention is paid on the relevance assumption. Relevance condition, or the covariance, non-zero covariance condition, is important, but like we don't think seriously enough about this problem. So let's think about this. And by the way, to study that more theoretically, it is much more complicated. So I am not going to discuss the details about weak instrument. So by the way, so the problem we are going to consider here is that this is what we need. Covariance should be different from zero. So, and then remember, and when we considered multicollinearity problem, we had a similar problem. Multicollinearity problem means that the covariance correlation coefficient between two regressors should be different from 1 or -1, right? But the problem is, if their correlation is different from 1 but very close to 1, then still you have some problem in calculation. In computation, maybe it's like it is similar to the denominator equal to 0. So, and a similar problem arises in this case too, regarding the relevance assumption. So relevance assumption, covariance is different from 0. But what if it is different from 0 but very close to 0, like 0.0000001? Then theoretically there is no problem. In theory, it is different from 0, so you don't have any problem. But you may have some computational problems, or like even if you get your computation may go through, but the results may be very inaccurate. So we are going to discuss this problem. We call this weak instrument. So an instrument is weak if its correlation with the endogenous variable is close to 0. So then think like so if the weak instrument is not a problem, then it is really easy to find an instrumental variable. So for example, generating an independent variable is really simple. You can just randomize. You can make a random number from any program. Then that is independent of everything in the world. So you may, if independence is the only assumption you need, then you may generate your random number and use that in your data. But the problem is the random number is obviously not relevant. It violates the relevance assumption. So we need to think about this. And to understand what's going on when you have covariance close to 0, we are going to consider the fitted value approach first. So in the fitted value approach, in the first stage regression model, in the first stage regression equation, you have this equation, but the problem here is gamma 2, the coefficient of Z2, the outside instrument. So x1 is just an exogenous variable included in the original regression equation, but Z2 is the variable that is excluded from the structural regression equation. So the coefficient of Z2 would be close to 0. By the way, gamma 1, the correlation between x1 and x2 does not matter. That's not a problem. They may be uncorrelated. Even if x1 is uncorrelated with x2, does not have any problem. It does not have any problem, but the problem is coming from gamma 2. And if gamma 2 is close to 0, then in the second stage regression, the problem here is x hat, which is defined as this guy, x hat does not have a component of Z2. So x hat will be almost identical to gamma 1 x1, right? If gamma 2 is 0. If gamma 2 is close to 0, so then x hat, x2 hat will be very close to gamma 1 x1, which is multicollinear with x1 beta 1. That's the problem. So, like again, you are using the variation from this part, but this part is basically equal to this guy, and you are using something gamma 1 x1 instead of x2. If you plug that into the place of x2, the problem is what you plug in is already on x1, and then there is another x1. So they are multicollinearity. So near multicollinearity problem happens, and then you see all the problems coming from the near multicollinearity. It is not exactly, so the correlation between x1 and x2 hat, it won't be 1, exactly 1, as long as gamma 2 is not 0. But as gamma 2 converges to 0, as it becomes more close to 0, those two guys, the correlation between those two guys will become closer to 1. So near multicollinearity problem arises, and going back to the discussion we had in the previous chapter. And if you move to the IV approach, remember the IV moment approach, you have basically its solution to this equation, but in what you have is here you are multiplying some matrix C and take inverse, but no matter what matrix you multiply C, its inverse may not exist. Its determinant will be close to 0, so the inverse is very, very inaccurate. It's like denominator will become very close to 0 no matter what matrix you use. So that is also very similar to what we discussed in the near multicollinearity problem. So then again, the symptoms in this case, weak instrument, when you have a weak instrument, the symptoms are very similar to what you see from the near multicollinearity problem. The coefficients of endogenous variables are very, very inaccurate, and that's reflected to large standard errors. The standard errors will be really large because the denominator is close to 0, right? And here is an example. Interestingly, the example is the example that I gave you earlier. So Angrist and Kruger's use a quarter of birth for estimation of the effect of education on wage is also a good example of weak instrument. So that paper was published in 1991. At that time, it was sensational. It was revolutionary. It's a very clever idea. But later on, many people have studied, had made follow-up studies on the same topic with the same data. But people realize these kind of weak instrument problem later, after they used a very revolutionary method. But later on, people like economists find this method could have a potential weak instrument problem, because even though maybe you may think quarter birth, how much quarter birth can affect your education decision? Frankly, it's very weak. The quarter birth may be one of the determinants of the education, but even if it is one of them, but it's a very minor, very small determinant. So that means the correlation between quarter birth and education is weak. And then, so many people criticized the original work, but still the idea is true. Idea is the idea behind quarter birth and education is not wrong. Then how do we check the weak instrument? It's easy. It's really easy, because you observe X and Z at the same time. Both are observed. So assumptions on observed variables can be tested easily by checking how they behave. So literally calculate covariance. If you have scalar endogenous variable and scalar instrument, simply you can calculate the covariance and check whether the covariance is 0 or not, close to 0 or not. Alternatively, more actually as easy as that is to estimate the first stage regression. If you use the fitted value approach or not, just estimate the reduced form regression of x2 endogenous variable on exogenous variable and instrument. And then you can test whether the coefficient gamma 2 is significant or not. If gamma 2 is significant, statistically significant, that means gamma 2 is different from 0, statistically different from 0. Otherwise, if you find gamma 2 insignificant, you have problem. Right? It's really easy. So it's pretty easy. And when you have and if you extend that idea to more general case, suppose that x2 is an endogenous variable with one dimension. Suppose that you have one endogenous variables and assume that there are, say, 5 instruments. One endogenous variable with 5 instruments. Then what you need to do here is not testing the significance of each of the coefficients. There will be 5 coefficients in this regression. You need to test, but you can test the joint test of the 5 coefficients. The joint hypothesis that all of them are 0 or not. If some of them is not 0, that's enough. So what you need to do in general, in the most general case, is check the joint significance of the coefficients on the excluded instrumental variables. The joint significance test, like F test. And the F test, rule of thumb is that the F statistic on gamma 2 should be greater than 10. It's a kind of rule of thumb. So if it's greater than 10, okay, that's okay, approximately okay. And less than 10, then need to think about whether it's weak or not. Think about that. Then when you find a weak instrument problem in your data, what can you do? Nothing. Simply there is nothing you can do. Of course, you may want to find a better instrument, or you want to collect more data, but both of which are not usually possible. If you could do better, then simply it's not your option in most cases. You cannot collect, you cannot make your own data. So these two are not the options. Alternatively, there are econometric theories, which is non-standard asymptotic theories for weak instrument. Like the most famous paper is by Steger and Stock, 97. But it's hard to understand, and it's theoretically okay, but I have not seen, it's not that popular in applied work. because it's too theoretical, and frankly, I think it's not that intuitive how it works. So so my conclusion is, if you have a weak instrument, then you are screwed. So you cannot do anything. That's a simple conclusion. Okay, then in the next video, I'm going to talk about what happens when you have too many IV. So see you in the next video.